Hello everyone. In today's lecture, we are going to learn about the process of performing a two-way ANOVA. We are going to learn what it is, how it is different from one-way analysis of variance, and we'll go into the logic that we use to perform a two-way ANOVA analysis. Now, the one-way ANOVA that we studied before taught us how we can compare the means from three or more populations. So we worked with an example where we studied the mean energy consumption across different regions of the United States, the Northeast, Midwest, South, and West, if you remember. And it would let us test whether region alone has a significant effect on energy usage. That was an instance of a one-way ANOVA analysis. We just focused on the region from which the sample was drawn, took measurements from the different regions on the energy consumption, and we did a comparison of the means. However, there can be situations where it's not just the geography that affects the energy consumption, not just the regions from which the sample was drawn, but also the season, the winter, spring, summer, or fall. What would be the effect of region if the season or the climate of the region was also taken into consideration? For example, maybe the South consumes more energy in summer due to air conditioning, while the Northeast spikes in winter due to heating. For situations like this, we cannot use the one-way ANOVA. We will have to fall back on the two-way ANOVA analysis. With the two-way ANOVA, we can analyze how two independent factors, in this example that I'm giving you, region and season, would impact the variable of energy consumption. At the same time, we can even test for interaction effect. So the question that a two-way ANOVA will help us answer is, does region affect energy consumption? Does season alone affect energy consumption? Or do both those factors have an interaction effect? Does the impact of region depend on the season or the climate of the region? So we will talk more about those. We will learn how to interpret the main effects, the interaction effects, and do a complete two-way analysis of variance. Now, a two-way ANOVA helps us determine the effect of two independent variables or factors on a certain response variable that we want to study. When we learned about one-way ANOVA previously, we used an example where we studied the effect of different regions on the energy consumption of households in that area. In that case, we had only one independent variable, which was the region. I'm going to pull up the table that we used to do that one-way ANOVA study here and talk about it a little more. So here we have the table. If you recall, we had the US, the country, divided into four regions: Northeast, Midwest, South, and West, and these were the numbers from the samples from these regions, and we found their respective means, and we performed a one-way ANOVA analysis to determine if there was a difference in the means between the regions, if the regions had a role to play in the difference between the means. So there we considered only one dependent variable, which was the region. Now let's say that it's not just the region that affects the energy consumption, but the season also affects the energy consumption. For example, in the northern regions, there's more energy consumption in the winter because of heating. In the summer, there may be more energy consumption in the southern region because of the usage of air conditioning. So there we would see that there are two factors playing a role. One would be the region, and the second factor would be the season. So we would perform a two-way ANOVA study would help us determine whether just region by itself has an effect in determining the energy consumption, or is it the season by itself that affects the difference in the means between regions, or is there an interaction between the two factors? That is the region and the season, do they both have an effect on the energy consumption? All right. So in other words, we have the main effects where we study the effect of a single factor on the response variable, and the other one is called the interaction effect, where we want to know whether the impact of the first factor also depends on the second factor. Does the impact of region also depend on the season, for example, in determining the energy consumption, right? We will now talk about some of the key terminologies that we will be using and referring to in our study of two-way ANOVA. We will start with understanding what a factor is. A factor is an independent variable which affects the particular variable that we are studying. For example, in our example of different regions affecting the mean energy consumption, the independent variable was the region. The region was the independent variable. We wanted to know whether the region had an impact on the energy consumption, and there was just one independent variable in that case. The next one is the level. Each factor in two-way ANOVA, we will be working with two factors or two independent variables, and each of those factors will have several levels within themselves. For example, in the factor of the regions of the US, the different levels were the four different regions from which we drew our samples, right? So Northeast, and then there was the Midwest, the South, and the West. These were the four levels within the factor of the region, right? Within the independent variable, there were four levels. And then the response variable was the energy consumption, what we are measuring, what we are studying. And then the interaction is when the effect of one factor depends on the level of the second factor. That is the interaction between the two factors. Now, over here they have mentioned a different example. For example, if we want to study the effect of diet and exercise together on weight loss. So over here, look at this example below. We want to study the effect of diet as the first factor, the first independent variable. And then the second factor is the exercise frequency. All right. So within factor A, which is type of diet, we have two levels, vegetarian and non-vegetarian. Within factor B, again, we have two levels, low frequency exercise and high frequency exercise. And what is our response variable here? What are we measuring here? That's the weight loss. So we want to study whether diet types have an effect on weight loss by itself, or whether it's exercise and its frequency which determines the weight loss, or whether both have an impact on weight loss, right? Whether the type of diet is also affected by the exercise frequency to determine difference in weight loss. All right, so this is an example which we will go through in future slides as well. Now, before we proceed further, there's another terminology that we need to understand, and that's factorial design. Now, since a two-way ANOVA is involved with two factors, the design of the experiments are known as factorial design. So a factorial design involves two or more factors, each with multiple levels. So in two-way ANOVA, there are two factors and each factor may have multiple levels. Factor A may have A number of levels, factor B may have B number of levels, and therefore we say the experiment includes A times B combinations of these factor levels. So when we are asked to describe a factorial design of an experiment, we have to look at the levels within each factor. If an experiment has two levels in factor A and two levels in factor B, then the factorial design is described as a 2 by 2 design. 2 times 2 design, and that will also tell us that there are going to be 4 cells in the experimental design. Likewise, if an experiment has 2 levels in factor A but 3 levels in factor B, then the factorial design is described to be a 2 by 3 structure of the experiment. And 2 times 3 would tell us that there are 6 cells in the matrix that we form with the two factors. All right? Now let's try to understand what we mean by the main effect of each individual factor versus the interaction effect, which is between the two independent variables or independent factors. So it says here, suppose we have two factors A and B, each fixed at two levels, high and low. So in this table, we have two factors. One factor A is across the rows, and then we have factor B, which are the columns. And each of these factors have two levels. The first one is the low level, the next one is the high level. For factor B also, we just use generically the two levels as low and high. So I'm going to write here, this is the low for A and then the high for A across the rows. And then for factor B, this is the low for factor B and the high for factor B as well. Now, when we are talking about the main effect of factor A, right? The main effect of factor A is the difference between the mean values of the response variable when factor A is set at high and at low. So when we consider the main effect on factor A, what we do is we find the average of all the values associated with low of factor A. So 5, 3, 6, 8. Irrespective of whether factor B is high or low, doesn't matter. For the time being, when we consider just factor A, forget about factor B. Just take all the values associated with low of A, right? And find its mean, find the average. And then do the same for the high level for factor A and find the average of all the values across both levels of factor B. All right, we are just ignoring factor B at this point. We only consider factor A, and then we will find the mean of each of these levels for factor A, which they have done here. All right, they have first found the mean of high, which is 8 plus 4, 8 plus 4 plus 18 plus 17 divided by 4. That's how you find the mean or the average of values. And you do the same for the level which is low A. So 5 plus 3 plus 6 plus 8, that's what they have done here, divided by 4. And then they have found the difference between the two means. So we have factor A high mean and then factor A low mean, and then we find their difference, and it tells us the difference is 6.25 units. So that gives us the main effect on factor A, where we have completely ignored the influence of factor B, found the mean of all the low-level factor A values, the mean of all the high level factor A values, and we subtracted the low from the high, and we came up with this number 6.25. So it says here increasing factor A from low level to high level increases the value of the response variable by 6.25 units on average. So that is how we study the influence or the main effect of a particular factor. Now, as for the main effect of factor B, it's the same process as factor A, except that now we just consider the average of the values under low B's and the average of the values under high B, and then we subtract the low B average from the high B average. All right, so that's what they've done here. First, they have found the average of all the highs under factor B, which would be 6 plus 8 plus 18 plus 17. That's what they have here. And then the average of the low B's, which is 5 plus 3 plus 8 plus 4 divided by 4 gives the mean of that. And then they subtract the low from the high for a value of 7.25. So the conclusion is increasing factor B from low level to high level increases the value of the response variable by 7.25 units on average. To see the interaction effect between the factors, we will first look at one level or one factor and see how changing the other factor affects the value of the response variable, and we will go into that in the next slide. Now, to study the interaction effect between the two factors, factor A and factor B, first we will hold ourselves onto one level of factor B and compare the effects of factor A high and factor A low. So we will just focus on low B. We will ignore high for the moment. We will just focus on factor B low values and compare the means of factor A high and factor A low, and that's exactly what they've done here. They have taken just the values under low B. So 8 plus 4 divided by 2 gives the mean of high A's, and 5 plus 3 divided by 2 gives us the mean of factor A low, but only the values under factor B low. We completely ignore the factor B high. In the next slide, we will consider that as well. But for the first step, we just focus ourselves on low of B and compare the high and low of factor A. And we see there's a difference of 2 units when we change the level of factor A from low to high. right? So now let's see what happens if we hold on to factor B high and compare the lows and highs of factor A within the factor B high group, right? Now here we will perform the same process as before, except that this time we will hold onto the high level of factor B. So we will just look at the values within the high box under factor B and compare the high and lows of factor A. In other words, we will compare the mean of high A with that of low A within this box of high B. This is now our focus. We ignore the low B values at this point. All right. So what they've done here is they have taken the mean of high A's, but just within this box. So 18 plus 17 divided by 2 minus, they're comparing the two. So they subtract from the high values, the high mean, 6 plus 8 divided by 2, which is the mean of low A's, and that difference is 10.5 units, right? And this is how the interaction effect is studied. However, if there is an interaction between the two factors, it can cause some confusion. It says over here, if we are at the high level of factor B, is what we just did here, just within this box, increasing factor A from low to high increases the response variable by 10.5 units on average. However, the main effect of factor A was 6.25 units, if you recall, when we just looked at the main effect of factor A. That means the mean of all the high A's minus the mean of all the low A's, we got a difference of 6.25 units. That was the main effect. This can, however, be misleading because at the low level of factor B, correct, the mean increase in the response is only 2 units. But at the high level, it's 10.5 units. So that difference needs more study. It is kind of misleading. All right. Now let's try to determine the main effects and the interaction effect with a concrete example. So here we have an example where we are considering the weight loss based on diet, type of diet, as well as exercise. So there are two factors here. Factor A is the type of diet. So two types of diets are considered. So two levels, vegetarian and non-vegetarian. And for factor B, we have the exercise, a low intensity exercise and a high intensity exercise, right? And this makes it a 2 by 2 factorial design because there are two levels within factor A and two levels within factor B, which makes it a 2 by 2 factorial design. All right, so this particular experiment is based on a 2 by 2 factorial design. So if we consider the main effect of diet, so here we have the numbers over here. These represent the weight loss in kilograms. So with the vegetarian diet, if we want to consider the main effect of diet, we find the mean of all the values under vegetarian, irrespective of the level of exercise. Do not consider the level of exercise. We just look at the numbers that are in the row for vegetarian, find their mean. So 2 kilograms plus 4.5 kilograms, the mean of that is 3.25 kilograms, correct? And then for the non-vegetarian, again, just find the mean of all the numbers in the non-vegetarian row, and that gives us 2.25 kilograms. So we see over here that the vegetarian diet seems to be more effective in losing weight, correct? Just taking vegetarian over the non-vegetarian. So you lose more with the vegetarian diet according to the study. Now let's consider the main effect of exercise, which is factor B. So for that, we just focus on the mean of the low intensity exercise and that of the high intensity exercise and do a comparison of the means. We do not consider the diet at this point, all right? It's just the exercise effect that we are trying to study. So the mean of the low exercise weight loss was 1.75 kilograms. That of the high was 3.75 kilograms. So we see that over here with the high intensity exercise, irrespective of what diet one may be taking, right, the weight loss is much higher than with the low exercise program, correct? Now, for the interaction effect, it says the difference in weight loss between low and high exercise is greater for vegetarian than for non-vegetarian. So to understand the interaction effect, we focus just on vegetarian and compare the high and low intensity exercise numbers here. So high exercise minus low exercise will give us a weight loss of 2.5 kilograms, right? So this will give us 2.5 kilograms. So the difference in weight loss between high exercise and low exercise is 2.5 kilograms with the vegetarian diet. With the non-vegetarian diet, it's 3 minus 1.5 kilograms, correct? So that's 1.5 kilograms. 1.5 kilograms. So that tells us that there may be an interaction effect going on because we see that within a particular factor there is a difference in weight loss. Like it says here, the difference in weight loss between low and high exercise is greater for vegetarian diet than for non-vegetarian diet, and that suggests possible interaction effect. That means that vegetarian with high exercise is more effective in weight loss. So both factors play a role here, right? Therefore, here let's summarize what we learned about finding the main effect of the different factors as well as the interaction effect. So based on this table over here, we first considered the main effect of diet, which was factor 1, and we found that vegetarian diet leads to more weight loss than non-vegetarian diet across both exercise levels. So in order to find the main effect of factor 1 or diet, we looked at the mean weight loss across vegetarian diets and then for non-vegetarian diets, irrespective of the exercise level. And we found that vegetarian diet, no matter which exercise level one followed, resulted in greater weight loss than non-vegetarian diet. So we held the exercise level, that's factor B, constant, and we compared the difference between the two diets. As far as the main effect of factor B, which was exercise, we went by the columns. We found the mean weight loss for low exercise, we found the mean weight loss for high exercise, and we compared the two, and then we saw that high exercise leads to more weight loss than low exercise across both diets. No matter whether you are having a vegetarian diet or a non-vegetarian diet, based on this data, if you exercise at a high level, high intensity, the weight loss will be more than with the low exercise. So that suggests the main effect of exercise. Now let's look at the interaction effect. The difference in weight loss between low and high exercise is greater for vegetarian diet 2.5 kilograms. So that means if we subtract 2 from 4.5 kilograms, high minus low, then we get a difference of 2.5 kilograms of weight loss. Then for non-vegetarian, that difference is just 1.5 kilograms. So that suggests that there is a possible interaction effect between the two factors. Now let's use another example to reinforce our understanding of main effect and interaction effect. Now in this example, we are studying the effect of study method as well as study time on test scores. So the response variable here are test scores. These numbers are test scores 70, 75, 80, 85. And factor A is the study method. So the first level of the study method in factor A is just studying from the textbook. And the second method is using video lessons to study for a course or for a subject. The other factor, factor B, is study time. So one of them is short study time and the other one is longer study time. And these are the scores. So we are going to go over the main effects first of study time. For the main effect, when we are looking at the method, then we just compare the difference in times between the two methods. So I'm not going to take the means and then subtract here, although that's one way of doing it. But for this one, I'm going to just look at the difference in the scores for both these methods of study, textbook and video lessons. So we see for the first one over here, 80 minus 70 is 10. Right? And this difference is also 10, 85 minus 75. So video lessons is definitely more effective. It's an increase in test scores by 10 points using video lessons, irrespective of how much time one puts into their study. Video lessons consistently lead to higher scores than textbooks, so that suggests a main effect of study method. The other one is the study time, factor B. For that, we compare two values here, 75 minus 70 and 85 minus 80. Both of them have a better score if long study time is used, irrespective of whether they use the textbook method or the video lesson method. It shows longer study time improves scores across both methods. It suggests a main effect of study time. So longer study time does have a better effect on the scores than a shorter study time, regardless of what method has been used. For the interaction method, we see the improvement from short to long study time is equal for both methods, right? So 75 minus 70 is 5 units. 85 minus 80 is also 5 units. It's not that one is greater than the other. So the improvement from short to long study is equal for both methods. There's a 5-point gain, and that tells us that there's no interaction effect in this example. Now in the previous slide, we showed that there's no interaction effect. However, if we change the score for long study time and video lessons to 95, previously it was 85. If we change that to 95 and then compared the difference between 75 minus 70 was an improvement in score by 5 points, whereas 95 minus 80 is 15 points gain. Correct? So that tells us that there is an interaction effect. So when these differences are the same, then the conclusion is there is no interaction effect. However, if we see that one is greater than the other significantly, then the conclusion is there is an interaction effect, right? This shows there's an interaction effect impact of study time depends on the study method. Let's look at the way we should be stating our hypothesis in a two-way ANOVA. The null hypothesis is to be stated in three ways because we have to consider factor A, factor B, and the interaction between factor A and factor B. So we have to include all three in our null hypothesis statement in two-way ANOVA. We first have to say as part of null hypothesis that there's no effect of factor A. For factor B, it's the same. No effect. Factor B does not have any effect on the response variable. And then the third one is that there's no interaction between factors A and B. The alternative hypothesis will be at least one effect is significant. So factor A has an effect, factor B has an effect, and factor A and B both have an effect on the response variable. They have an effect on each other, right? So that is how we state our hypothesis in a two-way ANOVA. Now here we have been given a technology-generated two-way ANOVA table. We will go through the table one by one, all the cells, and try to understand what these values refer to. Now, this is an example of which we haven't been given any details, but we've been told that the response variable is perhaps the score on a test. And then there are two factors, the row factor or factor A, that we generally label the row factor as, is exam. And within that factor, there are multiple levels. We don't know what each of those levels are or how many they are yet. There's a way of telling that from this table, but at this point all we know is this is the row factor exam, and then within exam, within that factor, there are multiple levels. Could be different types of exam like online exams versus in-class on paper exams. And the other factor, which is also referred to as factor B, column factor, is lecture. So perhaps type of lecture or the length of the lecture, something like that. But the column factor also would have multiple levels within it. All right. So here is the ANOVA table. These are the different columns starting with the source. So under source, there is a row for the row factor, which is exam, and then there's one for factor B or the column factor, which is lecture. Then there is a row to determine the interaction, the data for the interaction between factor A and factor B. And then there is a row for the error calculation. And finally, we have a total row. So the next column is the degrees of freedom. There's one for exam, lecture, interaction, error, and the total degrees of freedom is the sum of all the degrees of freedom above it. The next column is some squares, and there's a value for each of these rows: exam, lecture, interaction, and error. And then there is the SST, or the total sum squared, and that is the sum of all these values, SS values, of the columns above or of the cells above. All right. And then this column here, MS, means the mean squares. All right, so sum of squares for the mean. Then we have MS cell for exam, which is treatment, right? Exam is one of the factors. Then there is a lecture, which is second factor. Then we have an MS value for interaction, and then of course error. So this one here, 133.875, this value is really the MSE, error sum of the means. All right, so let me write that here. This is MSE. Now the calculation for MS values is this SS divided by the respective DF values. So to find the MS of exam, MST of exam, you just take the SS value for exam 18.05 divided by the corresponding degrees of freedom, which is 1. So 18.05 divided by 1 is 18.05, and that's why you see that value here. For lecture, it's the same thing. The SS for lecture divided by the corresponding degrees of freedom, which is 1, and that's why we have MS value of 0.45. Interaction, again, same thing. Because all of these DFs are 1, therefore the SS and MS values are the same. But normally, if degrees of freedom is something other than 1, then the MS and SS values will be different, right? The next column is the F statistic value. The formula for the F statistic value is MST over MSE. All right, so here the MSE value is 133.875. So this F-stat value for exam, which is 0.1348, was calculated by taking this 18.05, which is the MST value for exam, and dividing it by 133.875, the MSE value. Likewise, for lecture, this F-stat value was obtained by dividing 0.45, the MS for lecture value, divided by MSE, which is 133.875, and the same for the interaction F-stat value. And once we have the F-stat values, we have our P values, which we can obtain again using technology. Now, as we see that here, that 0.7183 is a pretty high P value, especially when we perform a test at the 5% significance level. Alpha is 0.05 compared to 0.05.71 is a pretty high value. So this would mean that we will not reject the null hypothesis, which will say that the exams do not affect the response variable. Same thing for lecture. The p-value is 0.9545, which is extremely high. But look at the interaction value, which is 0.0032. That tells us that there is an interaction between these two factors, right? So we will go into more details later on, but in the next slide I want to go over the formula that we use to calculate these degrees of freedom for each of these sources. Now here is another two-way ANOVA table generated using technology. So we will go through this one, and here we have some missing values that we need to fill in. So I will go over the process of doing that, and we will also look at the degrees of freedom calculations for each of the degrees of freedom for the different sources. Right now, let's look at the degrees of freedom calculations. For the factors, the formula to calculate the degrees of freedom is number of levels within that factor minus 1. So here we see that the degrees of freedom for factor A is a 2. That tells us that the number of levels within factor A must be a 3, because the DEF was obtained using the formula number of levels minus 1. So they had to subtract 1 from the number of levels under factor A to get 2. So that means the number of levels within factor A must have been 3. The same for factor B. It's the same formula, number of levels within factor B minus 1. So if the DEF is a 2, then the number of levels within factor B must also have been a 3. Right? And then the interaction factors is the DF for factor A multiplied by the DF of factor B. For factor A, the DF is 2. For factor B, it's 2 also. So 2 multiplied by 2 is a 4. Now be careful. 2 plus 2 is also a 4. So for this particular purpose, whether you multiply or add, you still get the 4. But if it was something else, 3 and 3, then you should multiply the numbers to get the interaction df's. 3 times 3 would be a 9 in that case. All right. Now the error df is 27 here. How did they come up with this number? The formula to find the error df is the number of observations in each cell minus 1. So within each cell, how many observations were captured? From that, you have to subtract 1. So that would be kind of n minus 1. But that n represents the sample size within each cell multiplied by the total number of cells in the ANOVA design, in the factorial design, so to speak. All right. And this formula is true only for balanced design. What we mean by balanced design is the number of observations within each cell will be the same. There'll be an equal number of observations across all the cells. So only in that situation this formula would apply. All right, we will not discuss the formula for unbalanced design. For our purposes, let's just focus on balanced design. So it's number of observations in each cell minus 1 times total number of cells. So the total number of cells here would be 3 times 3, correct? So the total number of cells in this design would be 3 levels for factor A multiplied by 3 levels within factor B, and that would be 9 cells, right? So total number of cells is 9. So number of observations in each cell minus 1. So if that is 9 and the result is 27, then the number of observations in each cell minus 1 must have been a 3, right? So that is the number of observations in each cell minus 1. Therefore, the number of observations in each cell must have been a 4. There must have been 4 observations per cell, and that gave us n minus 1, 4 minus 1, as 3 for number of observations in each cell minus 1 multiplied by the total number of cells, which was a 9, and that's how they came up with an error df of 27. All right. Now the next part here, the total for df is left as blank. We have to fill that in. So all you need to do is sum up the values 27 plus 4 plus 2 plus 2, and that will give you the total df, and that should be a value of 35. All right, so A will be 35. Right, just sum up these values. Then we have the total for B, to SST or SS total will be the sum of 2269.8, 115.2, 1694.8, and 860. And when you sum them up, you should get a value for B, which comes out to be 4939.8. All right. Next, we have to fill in the value for C, and that's MS, correct? That's MS here. So we have to find the MST for factor B. What is the formula for MS? It's SS. So let's write that down here. For MST, for the factors, it's going to be SS divided by the corresponding DF value. So SS is 115.2 in that row, and the DF is a 2, which gives us a value of 57.6 for C. All right, so that is how the calculation came up. Right, so this is 57.6 is 115.2 divided by 2. What about D? D is the F statistic corresponding to factor A. The formula for the F stat is MST over MSE. Now here the MSE has a value of 198. This is our MSE. So you just take the numbers of MS for each of these sources, all right, for each of these sources. So for D, it would be 1134.9 divided by 198. So I'm going to write that here. It's going to be 1134.9 divided by 198. This is the MSE value, and that will give us a value of 5.73. 5.73. Likewise, to find the value of E, you will have to take 57.6, the value of C that we just found, and divide it by 198, right? So that would be 0.2909, and finally F would have a value of 0.3939. All right, and we found that by taking the 78 for the MS of interaction and dividing it by 198. We came up with a value of 0.3939. And here are the corresponding p-values for factor A, factor B, and interaction values. We see that factor A p-value is pretty low. It's 0.000. So is the interaction factor. But for factor B, the p-value is pretty high, 0.183. So we see here factor B has a p-value which is pretty high, 0.183. So we do not reject the null hypothesis in this case. That tells us that factor B does not have an effect on the response variable. However, based on the p-value of factor A, it does have an effect on the response variable. And this one, 0.000, tells us that there is an interaction between factor A and factor B, right?